Okay. So, hope everyone is back. Let's consider in regime 1 between y equals 0 and y equals 10 meters. In that interval, what was the work that was being done by gravity? Andreas?
I'm not entirely sure on the accuracy of my answer, but I got 7,800 joules.
Okay. Well, gravity is acting downward. The body is moving upward. So it's minus mgh. So 80 kilograms times 10 meters. Let's let G equal 10 just so we can do the math in our heads. In which case we will get 8,000 joules. Is that right?
Yes.
Okay. So these are all in joules. So 8,000 joules. Now, Louis, what is the work that was done by the rescuers?
For the 0 to 10 range?
Yeah, actually that's not the right way to look at it. What is the total work done on the body? That's actually the one we need to do next. What is the total work that is done?
For that one, I got a total of negative 7,800.
Okay, for the total work done on the body. Well, let's use the work energy theorem. The total work done equals the change in kinetic energy. But the change in kinetic energy goes from speed 0 to 1 meter per second at the 10 meter mark. So that would be 1/2 m times v squared. So 1 meter per second squared, that's actually, the total work done is actually 40 joules, isn't it? Is that right?
Oh, I think I may have done it backwards. I did get 40, but my 40 was for work done by the rescuers.
Ah, okay, I see. Well, let's think about this. The total work total is always going to be equal to the work done by gravity plus the work done by the rescuers. So the work done total is given by the work energy theorem. And the work done by gravity right, the work done by gravity is, I put 8,000, and what's wrong here? Obviously, this is minus 8,000. Okay. So the work done by gravity is minus 8,000 joules. The total work done is 40. What's the work of the rescuers? What does that have to be? So Louis, go ahead.
It's positive 7,960.
No, I think it's 8,040. Because 8,040 minus 8,000 is 40. So 40 joules equals minus 8,000 joules. plus the work done by the rescuers. So the work done by the rescuers must be 8,040. Is that right? Okay. I'm sorry, Lou, you probably don't know that I'm addressing you. Is that right? Does that look right?
Yes, I think for the entire problem, I used a different equation. I used the one you gave us earlier that was mg times d.
Yes, but that was the work done by gravity. That's the work done by gravity. The work done by gravity is going to equal mg times delta y. But delta y minus mg delta y. So delta y is the 10 meters. G is, let's call it 10 to make the math easy. And the mass is 80, and there's a negative sign there. Why? Because the motion is upward and gravity acts downward. So you could say that gravity does negative out 8,000 joules of work on the person, or you could say the person does 8,000 joules of work on gravity. It's the same thing. All right, let's go to the second regime. What's the total work done between y equals 10 and y equals 90? Adam? And you can use this equation right here. Work total is change in kinetic energy.
I just need a second to.
So he's moving at 1 meter per second here. And at this point, he's still moving upward at 1 meter per second. So what's the change in kinetic energy?
None?
I'm sorry, I didn't hear you.
Is there no change if he's going the same?
Yes, there's no change in kinetic energy. Therefore, there's no total work. So the total work is 0. Now, what was the work done by gravity? Well, the work done by gravity is 80 kilograms times g times, this is 80 meters, right?
So it's 64,000
Yeah,
or negative 64,000.
negative 64,000 joules. So the work done by the rescuers must be what, Benjamin?
64,000.
Positive 64,000. Okay, Truck,
In your table, I have a question.
yes.
You have you filled in the section 3 first. So is that the work? Do we start on number 3 and not number 1?
You have to start wherever you have to figure it all out, knowing that this is the work done by gravity, and this is the total work, and this is the total work. So start wherever it seems most convenient to you.
He's
It's
saying
on the
that
table.
your regimes are backwards on the table. It should be 3, 2, 1, not 1, 2, 3.
Good Lord. So this is regime 1, this is regime 2, and this is regime 3. Thank you. Gosh. Okay. Truck.
For the work of gravity, I have positive 8,000.
Is it 8,000 or minus 8,000?
Oh, minus 8,000. Sorry, I forgot the minus sign.
Okay, that's important. So Aman, can you tell me what the total work is? What is the total work here in regime 3, up here at the top? So in going from 1 meter per second to 0 meters per second, can you tell me the total work that was done? Okay, well, we use this equation. The total work done is the change in kinetic energy. And I go from 1 meter per second to 0 meters per second. So in regime 3, the total work has to be minus 1/2 m times 1 meter per second squared. And m is 80 kilograms. So what's the total work? Minus 40. That's right. Now, Christopher, what must therefore be the work done by the rescuers?
Negative 8,040.
No, we have the total work is minus 40. The work done by gravity is minus 8,000. What's the work done by the rescuers? Minus 40.
Negative 7,960.
Positive 7,960. The work done by the rescuers is always positive because they're pulling on the rope, up on the rope, and the guy is moving up.
Okay, I see. Thank you.
All right. Okay. Here are the things I want you to understand. You can calculate the work done by gravity very easily. You have to know whether you're moving up or down, and that determines what your negative sign is. You also have the work energy theorem, which tells you that the change in kinetic energy is equal to the total work. And then, of course, the total work is the sum of all the work done by all the forces that are acting. So the total work is the work of gravity plus the work of the rescuers. And in that way, you can fill out this form pretty easily. Now notice, I haven't said anything about the force with which the rescuers are pulling. They could jerk him off the ground, moving at 2 meters per second, then slow down and nearly stop, then jerk up again. And if they are at the end of this motion at y equals 10 meters, if they're moving at 1 meter per second, then the work that's done here only depends on the endpoints. You don't need to know anything about the forces that were on the rope here. So a test question would be, what's the work done by the rescuers? To know that, you have to know the total work and you have to know the work done by gravity, but you don't have to know anything about the forces. What's the average force that they pull on the rescuer here to accelerate him from 0 to 1 meter per second? Well, the work they did was 8,040 joules. So 8,040 joules, that has to equal the average force of the rescuers times the distance, which is 10 meters. So 804 newtons is what they had to exert on the rope on average. Shifa, what was the average force exerted between 10 meters and 90 meters? The average force exerted on the rope by the rescuers, or by the rope on the man, either way.
What was the question again? Do you mind
What is
repeating
the
it?
what was the average force of the rope on the guy in the stretcher between here and here?
100?
Well, 100 newtons. Well, does he accelerate between here and here? Isn't he going up at a constant speed of 1 meter per second? So if there's no net acceleration, what's the net force? Shiva, if there's no net acceleration, what's the net force?
Would be 0?
Right. So the force on the rope, because it's moving without accelerating, has to just be equal to the weight. So what's the weight of this guy? 80 kilograms times 10, let's say 800. So the average force from here to here exerted on the man by the rope is 800 newtons. So what is the average force exerted in the third regime here? Well, the work done by the rescuers is 7960 joules. That has to equal the average force times the 10 meters. So in this regime, the average force is 796 joules. So they pull with 804, I meant to say newtons. They pull with 804 newtons from the ground to 10 meters, then 800 newtons from 10 meters to 90, and then 796 newtons from 90 to the top. But we don't need to know what those forces are. We can calculate what the average forces are knowing the work. But we don't need to know them to fill out this form, do we? So the force could have varied. But we don't need to know that. I'm trying to impress on you that if we try to do the same calculation knowing the force as a function of y, it is generally a much more difficult problem to determine what speed he's going at or how much work is done by the rescuers and things like that. Okay, let's look at the inclined plane again. So here we have an inclined plane and we have a block. And let's say that this is the angle theta. This is the height h. And from the top of the wedge to the bottom is a distance d. Now, what is the work that is done dragging this block from here to here? Well, the force that I exert must be mg sine theta if I'm dragging it at constant speed. So let's say I'm dragging it at constant speed, so the acceleration is 0. So the force is just mg sine theta. Well, what is the work done going from here to here? Well, the work is just, now I'm not talking about the total work that's being done. I mean the work done by the person pulling on the rope. Well, that is just going to be mgd sine theta. Now let's do this problem in a different way. Let's say that we drag the block from here to here, and then we go straight up. The work that's done here is 0. I'm assuming it's a frictionless plane, okay? So to go from here to here doesn't require any work. To go from here to here, the work is mgh. But what is h? Isn't h just d sine theta? So I do the same amount of work going from here to here as going on this path. Let's ask the question in a little bit different way. What is the work done by gravity in going from here to here? Well, the work done by gravity is just minus mgd sine theta. And what is the work done by gravity going from here to here, then here to here? It's exactly the same thing. So the point I'm trying to make is that the work done by gravity is independent of the path that the object takes. So that tells me something. This is a demonstration of the fact that the work integral for gravity is path independent. So this is my integral. The gravitational force dot dr. That integral does not depend upon the path I take. I can go from here to here, or I could go like this, or I could go like this, or I could take any other path imaginable. And if I end up at the same place, I get the same exact result for the integral. So for gravity, the work integral is path independent. Now that is a very special thing. Integrals which are path independent, or forces for which the work integral is path independent, are called conservative forces. And not all forces are conservative. The work integral for friction is not path independent. Let's consider friction for a minute. I put a book on a table and I push it out a ways. Work is being done by friction opposing the motion. I bring it back to the same place and friction still opposes the motion. I should draw a picture for this. So here's the tabletop looking down from above. And here's my book. My frictional force always opposes the motion. So I go from here to here and then back again. If this is a distance d, my total work is equal to the frictional force times d, 2d. So I go out d and come back. Because friction always opposes the motion. So the work done by friction is negative as well, minus 2fd. Now let's say instead that I go out here to a distance 2d and then come back. Then my work done by friction is going to be minus 4FD. So the work integral for friction is not path independent. I go here and I end up here and I do a certain amount of friction, of work. I start here, go out here and come back, and the work done by friction is different, even though the endpoints are the same. So friction is not a conservative force, but gravity is. So for a conservative force, we have that the work integral F dot dr is path independent. Now we also have that the work integral around a closed path is always identically zero. Let's consider the case of the block here. Let's say that I went up to the top. The work done by gravity is minus mgd. I come back down, the work done by gravity, I'm sorry, mgd sine theta, is positive mgd sine theta. So my work over this closed path is zero. What about this path? I go here and here and here. Well, now my total work is zero for gravity minus mgh, which is minus mgd sine theta. And then down here is plus mgd sine theta. So the integral is zero. So for a closed path, my work integral is always zero if it's a conservative force. There's another thing that is also true, and that is that the curl is identically zero in all space. Now, we haven't introduced you to this yet, but I will. We also have that the force can be derived from a potential energy function. So if one of these statements is true, any one of these, conservative, path independent, circulation zero, curl zero, derivable from a potential function, if any one of those things is true, all of them are true. So let's, excuse me. Let me introduce you to the idea of the gradient operator. The gradient operator is in rectangular coordinates this. Okay, this operator has no meaning unless it operates on something. And one of, so let's say that it operates on a potential energy function. So I'm telling you that the force is equal to the negative of the gradient operator operating on U, which is just this. So U is a function of X, Y, and Z. Okay, now what about the curl? Well, the curl is kind of a funny thing. That is given by this determinant. I have my I, J, and K vectors. and I have the derivative with respect to x, the derivative with respect to y, and the derivative with respect to z, then f sub x, f sub y, and f sub z. Okay, so let's see if the curl of our force of gravity is equal to 0. So what is F? Well, F is minus mg in the j direction, isn't it? Because it acts downward in the minus y direction, and it's just equal to a constant, mg. Well, obviously, this thing is going to be 0 because the derivative of a constant is 0. How do I expand out this? I take I starting right here, cross out, and now d dy of fc, so d of fz dy, so I go this direction, then I go that direction, and it's a minus sign, dfy dz. Then I go to the next term. I put a minus sign in front. I cross out this. Now I have df of z dx minus df of x dz. Then I go to the next term, plus k, cross this out, and I get this acting on this, dfy dx minus dfx dy. Okay, well, all of these terms are 0 identically because f is a constant vector acting in the minus y direction. So any force which is a constant force is going to be a conservative force. It turns out gravity is also a conservative force when we study the universal law of gravitation. And we have the actual gravitational force between two bodies as a function of distance. That will also turn out to be conservative. All right, I think I may have fire hosed you a little bit here, and I'm sorry. Let's go back here and recap. Okay, so the work from the example of this inclined plane, the work done by gravity is conservative because if I go all the way around a closed path, I end up with 0 for the work. Also, the work is path independent. So I can go up or I can do this and I get the same work. Now, I've just shown you that the gravitational force has a 0 curl. I haven't yet discussed this part. Okay. So I need to define what the potential energy function is. Well, the potential energy function, the change in potential energy is just minus the work performed. So let's look at gravity again. Here's the height, y equals 0. Here is y equals h. Gravity acts downward, mg in the j direction. What is the change in potential energy going from y equals 0 to y equals h? Well, my motion is in the plus y direction. My force is in the negative direction. So the work done by gravity is equal to minus mg. Let's just call this y instead of calling it h. Y. So whatever height y I go to, my work done by gravity is minus mgy. So what is the change in potential energy between 0 and y? That's just negative the work is just mgy. So the potential energy is negative the work. In this case, it's mgy. And what is the force? Well, the force is equal to minus, in the I direction, d of mg, I'm sorry, in the j direction, mgy dy, which is nothing but minus mg in the j direction. So my force is derivable from a potential function. So that also tells me it's conservative. All right, we've actually gotten a little bit ahead of ourselves. But I want to reiterate these things. Gravity is a conservative force. A conservative force is path independent. The integral over a closed path is equal to 0. That's called the circulation. The circulation is 0. The curl is 0, and the curl is this strange differential operator that's given by this right here. And we calculate the curl by using a mnemonic device and a determinant. Okay. The other thing is that the conservative force is derivable from a potential function. And I just showed you that it was, where the potential energy function is minus the work. So the change in potential energy is minus the work. Okay, let's put the potential energy function aside for a moment. And let's look at Hooke's law. So Hooke's law, that is the spring force law. And it is that the force is minus kx. So here's a spring. Here's the mass on a spring at x equals 0, which is, I'm going to define x equals 0 as the equilibrium position of the spring, and I stretch it out to a distance x. Well, the magnitude of the force is kx, but it's called a restoring force because it acts to restore the body back to its equilibrium position. So my extension is in the positive x direction, but my force is in the negative x direction. So I could write this like this if I wanted to write it as a vector equation. What if I compress the spring? Well, if I compress the spring till it's at a position minus x, then the force is equal to minus k times minus x. And now I have a positive force. What does that mean? The force is in the positive direction, pushing the mass back to equilibrium. That's Hooke's law. Now, what is the work that's done by the spring when the spring is extended to a distance x, to a position x? Well, it's from x equals 0 to, let's call this x1, to x1 of the spring force, F for the spring, dot dx. Well, dx goes in this direction. The spring force goes in that direction. So the work is minus 0 to x1 kx dx. And that is obviously minus 1/2 kx squared. So that's the work done by the spring force starting at 0 at the equilibrium position and going to a position, I called this x1, x1. So the work done by the spring on the mass is always negative. At least if I start at equilibrium and go to some position on either side of it. The work done going to minus x1 is also negative because the displacement is that way and the force is that way. Okay, so that's Hooke's law. Let's do an interesting problem. Let's say that I have a frictionless floor and attached to this wall, I have a spring, and let's just put a little thing on the end there. And I'm going to treat this as an ideal spring. None of this has any mass. I have a block of mass m that is moving with a speed v0. It hits the end of the spring and it will compress it. What is the distance d to which the spring is compressed? We're going to use the work energy theorem. So we have that the total work done by the spring in compressing from here to here is minus 1/2 k d squared. That's the total work done by the spring force. What is the change in kinetic energy? Is minus 1/2 m v0 squared. So the distance that it compresses, d, is equal to m over k square root times v0. That was really easy, wasn't it? To do this in terms of kinematics, I need to know what the force is, then I know the acceleration. I have an initial speed of v0. I know my acceleration. How far does it travel if it's being decelerated? Okay, that's not really a hard problem, but it's a lot harder than writing this down. So the work energy theorem makes a lot of calculations very simple. Let's do a slightly more interesting problem. Let's say that I have attached to the floor a spring, and I have a little plate on it, but I'm going to assume that the plate and the spring have no mass, so they're in equilibrium right here at, let's say, y equals 0. Now I'm going to drop a block from rest from the height h, and I'm going to ask how far y equals minus d, and this is y equals h up here. How far does that spring compress? Well, the total work done on the block is equal to the change in kinetic energy of the block. So the change in kinetic energy of the block, well, it has 0 kinetic energy when I drop it, and it has 0 kinetic energy down here when the spring is at maximum compression. So the total change in kinetic energy must be 0. Well, that must equal the total work. The total work done by all forces on the block must be 0. Well, what is the work done by gravity? The work done by gravity, I'm dropping it from a height h, it goes to 0, but it also goes down to minus d. So the work done by gravity must be mg times the distance that it goes here, which is h plus d. Now, what about the work done by the spring? The work done by the spring is negative 1/2 k d squared. That means that W of gravity plus the work of the spring must equal 0. My equation is mg h plus d minus 1/2 k d squared equals 0. So now all I have to do is solve for d. And this is a quadratic equation in d. The quadratic equation is minus 1/2 k d squared plus mg d plus mgh is equal to 0. You can use the quadratic formula on that to determine the value for d. Now I'm treating d as an inherently positive quantity and y is equal to minus d. So when you solve this, you keep the positive value of d. And that's how far the spring is compressed. Okay. Now let me ask you this. Is the spring force a conservative force? Well, if I take my mass on the end of a spring and I move it out here, the work done by the spring force in going from here to here is minus 1/2 k x1 squared. Now, if I let the box go back to the origin, now the work done by the spring force is plus 1/2 k x1 squared. Obviously, that's equal to 0. So if I return back to my original position, that is, if my work integral is on a closed path, my work integral is 0 for a closed path. So that kind of tells me that the spring force is going to be a conservative force. Well, let's see if we can show that the spring force is derivable from a potential. The work of the spring force is minus 1/2 k x squared, where x is the displacement. The change in potential energy from the origin is equal to 1/2 k x squared, because the potential energy is the negative of the work. So is the spring force F equal to minus du dx in the I direction? Well, let's put in this for u. The derivative of this is kx, and the spring force is minus in the I direction kx. So I recover the spring force from a potential energy function. Therefore, it must be a conservative force. So the spring force is a conservative force. We have one other thing to discuss. It's a little bit of an odds and ends. But I want to discuss with you the idea of power. Power is equal to the work done divided by the time. And I can write this. This is the total work done divided by the total time. I can write it as dW dt. This is the average power. This would be the instantaneous power. So power is work done divided by the time. So let's write that down. Power is work, which is the integral F dot dr. So the derivative of this dt, well, I'm going to write that as integral of F dot dr dt. So the power is just the force divided with the velocity. So F dot V, and I actually get rid of the integral sign here because I've got a derivative here. Sorry about that. It's just F dot V. So let's say I have a ship. Here's the ocean. Here's my ship. And let's say that the drag force due to the water is a certain F. Well, if this ship is going to move forward at a speed V, at a constant speed V, then the force exerted by the propellers must be the same as the drag force. So the power needed to drive a ship with a constant speed V is just the drag force times V. So the slower I go, the less power I need. Eventually, I will be turning my propellers and the engines on the ship exerting all of the power that they are able to. And when that power is equal to F times V, then that's going to tell me what the maximum speed is. So I have to know what the drag force is as a function of V. But if I know the maximum speed, then I must know what the drag force is on the ship at that speed if I know the power necessary to turn these propellers. So look it up. Look up on Wikipedia. What is the maximum power to the propellers for an aircraft carrier? Just just Google an aircraft carrier like the USS Enterprise or something. Determine what the maximum power of the engines to the propellers are. Determine what the maximum speed of the ship through the water is. That'll be given in Wikipedia. Now you know what the drag force is on the ship. Okay. So that's it. That's chapter 6. Pretty simple, huh? First, let me ask if there are any questions on chapter 6. Chapter 6 is the work energy theorem. Okay, let's do some problems. Oh, this is a good one. 671. I'm just going to read it to you. So there's a table, and this table is frictionless. And I have a block here of mass M, and a cord goes through a hole in the table, and I can pull on it. This mass is going in a circular motion. Okay, initially, this mass is revolving with a speed v1 and at a radius r1. Now the cord is pulled from below, shortening the radius of the circle so that the block revolves at an r2 and with a different speed v2. And what they want to know is how much work was done by the person who pulled on the cord. Well, isn't the total work equal to the change in kinetic energy? So I could determine the tension in the cord when it's revolving at R1, and I could determine the tension in the cord when it's revolving at R2. Then I could determine the difference in the force. That must be the force with which I'm pulling down. And it would be very difficult. But what is the total work done? That's very easy. The change in kinetic energy is just 1/2 m v2 squared minus 1/2 m v1 squared. So in this problem, they ask you for the tension in the cord, T1, and they ask you for the tension in the cord, T2. Now, they ask you what was the work done by the person pulling on the cord, and they're trying to trick you into doing something difficult. They're trying to trick you into somehow saying, well, okay, here is the tension as a function of the distance that I pull downward. And the distance I pull downward is just R2, R1 minus R2. So versus Y, the position of my hand. Well, at R1, I have a tension T1, and at R2, I have a tension T2. So if I draw a straight line between them, then my force as a function of Y, I can determine the work done as the integral from R1 to R2 of the force dy. Okay, well, forget it. You don't have to do all that work. You don't have to do anything like that. Energy methods will tell you almost immediately what is going on here. The change in kinetic energy is equal to this. That tells you what the total work is. Now, what was the average force with which I pulled down? Well, I can get that from the work because that's just the force times the distance. So I can get the average force almost for free. In fact, it'll be this value right there. But I can determine that value right there from this equation. Okay, that's a good problem. Let's look at another one. I've got a bridge that goes like this. and I have a bicycle. So I have a person on a bicycle, and the person and the bicycle together have a mass of 80 kilograms. When you reach the base of the bridge, you're traveling at 5 meters per second. So you have V1 here. Now, at the top of the bridge, you climbed a vertical distance here of 5.2 meters, and your speed is V2. So let's call this H. What is the total work done on you and your bicycle when you go from the base to the top of the bridge? Well, the total work done has got to be the change in kinetic energy. So it's 1/2 m V2 squared minus 1/2 m V1 squared. Now, what is the work done by gravity on you and your bicycle? Well, you've gone up a height 5.2 meters. So the work done by gravity is minus mgh. Now, here's the point of the problem. How much work did you do pedaling the bicycle in order to climb from here to the top? Well, that seems like an insoluble problem. I don't know. How hard am I pushing on the pedals? How far around a circle do my feet go pushing the pedals around? And with what force do I push them? You don't need to know any of that, because you know that the total work done is equal to the work done by gravity plus the work done from pedaling. So the total work is this. The work done by gravity is this. So the total work done by pedaling is just the total work minus the work done by gravity. We won't work out the numbers. Though you can work out the numbers in the problem. I think this actually, I assigned this one. Okay, does anyone have any questions on this? So you use the work energy theorem and you've used the definition of work to calculate the work done by gravity. But since you have this term and you have this term, you can figure out how much work is done by the person pedaling. Let's look at another problem. This is problem 681. Here I have a shelf. I have a pulley. I have a mass M1. And I have a mass M2. Okay. Now, there is friction here. And we have, at t equals 0, we have the masses moving at a speed v is equal to 0.9 meters per second. The block M2 falls a distance d. And d is equal to 2 meters. Okay, what is the coefficient of friction? Let's use the work energy theorem. Well, the work energy theorem says the total work is equal to the change in kinetic energy. But the change in kinetic energy is minus 1/2 m1 plus m2 times, let's call this V0, times V0 squared. Why is the total kinetic energy of the system equal to that? Well, M1 is moving with speed V0 and M2 is moving with speed V0 as well. But that total work must be equal to the work done by friction plus the work done by gravity. Well, what is the work done by friction? Well, the frictional force is minus mg mu, acting in that direction. The block is moving to the right. That's why I put the minus sign there. And it falls a distance d. So the frictional force is that. Now, what about the gravitational force? Well, the gravitational force, oh, this is M1, I'm sorry. Only M1. Now, the gravitational force, the block M2 is moving downward and the force is downward. So M2 GD. So putting it all together, I have minus 1/2 M1 plus M2 V0 squared must equal minus M1G mu D plus M2G D. And now you can solve for mu. Can you see how complicated this problem would be if you tried to do it dynamically using forces and kinematics? But how simple it is when we use energy methods. Okay, I really think that's enough for today. Does anybody have any questions, issues, concerns? Okay, get to work on MP chapter 5 and 6. And be prepared Wednesday for questions on chapter 5 and 6 MP, and also on PIP. And what is coming up on our schedule? Okay, I'm going to push chapter 5, Mastering Physics, to next Monday, and also the PIP to next Monday. Let's do the quiz on force and work on next Monday instead of Wednesday. So mark your calendars that we're pushing that forward. And then on Wednesday, what we'll do is answer questions on PIP and MP and have lecture on chapter 7. All right. Anybody have any questions? Okay, well then,
Sorry, Professor, could we speak after?
yes, we can.
Thank you.
So I'll wish everybody a good day and I'll see you on Wednesday.